Hello friend, welcome and good morning to you. So today I am available with a new video for heat transfer by means of conduction. This is the 13th video in the conduction heat transfer. The channel name is AVM Tech Android. You can see this is a QR code of the channel. By scanning this QR code also you can directly enter into this channel and then you can subscribe this channel, or you can write AVM Tech Android on YouTube and you can enter into this channel. Do not forget to subscribe this channel. Via this channel you can learn different technical subject at free of cost. So friend, today we are going to discuss about unsteady state heat transfer. So in the previous video we were discussed about steady state heat transfer, and now this video and next video are the video related to transient heat transfer or unsteady state heat transfer. So in this video we are going to discuss about unsteady state heat transfer. So you can see here we have to go for lump capacity analysis. These are the sketch for that. We will find out what is the dimensionless temperature variation for unsteady state heat transfer or transient heat transfer. We will also discuss about what is called exponential heating and exponential cooling, that is variation of temperature with reference to time. Plus we will discuss about characteristic dimension for, you can say, flat plate, long cylinder, sphere, cube, large plate, etc. So all these things which you can see at present, that will cover in the present video. The book which I am preferring at present is Heat Transfer by Dr. A.V. Mehta and Professor P.G. Choksi from Books India Publication House. So at present we have to discuss first what is called steady state, and then we have to discuss what is called unsteady state heat transfer. A solid body is said to be in steady state if its temperature does not vary with variation in time. That is, temperature is function of coordinate system. You can say for Cartesian coordinate system it is function of x, y, z. So in case of the steady state heat transfer, what you can see here is the temperature does not vary with variation in the time. But when we will talk about unsteady state heat transfer, you can see the surface temperature that will vary with variation in the time, and you can say this temperature is a function of x, y, z coordinate system plus time tau. So here you can see the temperature is a function of coordinate system only. It is not depend upon the time in case of steady state, whereas in case of this unsteady state or transient heat transfer, this temperature variation is a function of coordinates plus it is a function of time also. So you can see the same thing is mentioned here. The conduction of heat in transient or unsteady state refer to the transient condition wherein the temperature distribution and heat flow at any point of system vary continuously with the time. So here you can see temperature distribution and heat flow, that is T and Q, that is continuously vary with variation in the time. So why we have to go for transient heat transfer? So the unsteady state heat transfer is very common in all heating and cooling problems at the beginning of the system. The analysis of transient heat transfer or unsteady state heat transfer is of great interest to the engineers because of its wide spread. The examples are You can see, if we'll talk about material science, it is the heating and cooling of metallic billets, heat treatment of metal by quenching process. So what we are doing here is, you can say the rod is available at, you can say 200 or 300 degrees Celsius in the furnace. So now entire rod is at 200 or at 300 degrees Celsius, and all of a sudden we are dropping that rod into the bath where the water is, you can say, available at 30 degrees Celsius, or you can say a brine solution is available at you can say 30 or 40 degrees Celsius. So this rod, you can say, that is at 300 degrees Celsius, and this water or the brine solution is at 30 degrees Celsius, and we are inserting this into the solution. So it is called unsteady state heat transfer case. The other examples, you can see cooling of IC engine cylinder. When the engine is moving on the road, the cooling is observed. When engine is stopped, when there is a stationary engine, cooling is also observed. That is also unsteady state heat transfer, because temperature is continuously vary with variation in the time. Brick burning, starting and stopping of different heat exchange units, vulcanization of rubbers, cooling and freezing of the food, heating of the boiler tubes, rocket nozzle, etc. These are few examples which are related to industry, where we will observe the temperature that is continuously vary, the temperature that is continuously vary with variation in the time. So along with the coordinate, this temperature that will vary with variation in the time tau. So these are few examples of unsteady state heat transfer which we can see in the industry. Now your task is to find out what are the different examples which you can see in the real life where unsteady state heat transfer is observed. So whenever we have to handle unsteady state heat transfer problem, either it is in the real life or in the industry, we have to go either for approximation method, analytical method, product solution method, graphical method, use of transient temperature chart, that is called Hazelor chart, or we have to go for the numerical method. So at present we have to go for approximation method to solve the unsteady state heat transfer case. When you are in the final year, you are with elective subject advanced heat transfer, we will discuss about this transient temperature chart, that is called Hazelor chart, to study this unsteady state or transient heat transfer problems. So when we are talking about unsteady state heat transfer, you can see the unsteady state heat transfer that is divided in two parts, that is periodic variation and second is the non-periodic variation. So in both the cases, temperature that will vary with variation in the time, but you can say if we talk about the periodic variation, you can say in the periodic or transient steady state, the temperature within the system undergoes the periodic changes which are either irregular or regular, but definitely cyclic. This is definitely cyclic. The examples which we can consider are temperature variation of building during 24 hours. So you know that from the very early in the morning, the wall of the building, that's temperature start to rise. It is, you can say, maximum at 12 noon or at 1 o'clock. After that, slowly the temperature of building wall material that will start to decrease. That is a cyclic variation, and we can also, you can say, measure it. Second, the temperature variation in the surface of earth during 24 hours. So with the rise in the day, slowly the earth temperature will start to rise. In the night, the temperature is dropping, and that is cyclic one. Next, you can see the temperature variation in the cylinder of an IC engine. Next, you can see temperature variation in the heat processing of the regenerators. So friend, these are, you can say, some you can say examples which are of industrial application, or which we can see first two, that is in our routine life. These two are of industry. So what you have to do is you have to find out what are the other example other than these two where you will observe periodic variation, and that you have to write in the comment, or you have to prepare it for your competitive examination. Either it is your class test, it is your university exam, it is your technical test for any company, or you can say it is of UPSC or GPSC exam. Now the next thing which we have to discuss is non-periodic variation. So what is non-periodic variation? The temperature change that is not in cyclic form, or you can say it is following some non-linear function of the time, and the definite pattern is not repeated in the cycle. Means here the definite pattern is not observed, like heating of an ingot in the furnace. You can say furnace is at 1000 degrees Celsius, and all of a sudden you put a metallic rod which is at 30 degrees Celsius. So all of a sudden there is a drastic rise in the temperature is observed in the metallic billet. It may possible that now the furnace is at 200 degrees Celsius, the metallic rod is at, you can say, 30 degrees Celsius, and you put it in the furnace. So what you will observe is the pattern is not followed. Like cooling of metallic billet, bars and blanks for the hardening purpose. We are going for quenching and all these things where there is no pattern is observed. You cannot predict whether what happens in the next stage, or at what time what is the temperature. So now friend, we have to go for the next analysis related to unsteady state heat transfer, that is heat conduction in the solid having infinite thermal conductivity, that is negligible internal resistance, or that is called lump parameter analysis. So this is a very important question. So before we will go for lump parameter analysis, we have to understand 2 or 3 things, that include what is meaning of infinite thermal conductivity, or what is meaning of negligible internal resistance, what is called lump, and what is called lump parameter analysis. So the theory which you can see here is talking about all this part. So this theory we have to discuss, that is talking about transient heat transfer. We are talking about solid body where the temperature that will vary with variation in the time. So let us start to discuss about this theory. So you can see all the solid have finite value of thermal conductivity K, and when K is there, definitely it is offering some amount of resistance to the heat transfer, and always some temperature gradient is observed in the solid when the heat is transferred through it. That is known to us. So if the material is having very good thermal conductivity, means the resistance offered is negligible, temperature gradient is, you can say, according to that thermal conductivity or according to the resistance offered. But if we consider the case, that is if the physical size of a body is very small, that is for a solid of large thermal conductivity with the surface area is very large proportional to their volume, like the example include the plates, bar and thin metallic wires, where surface area is a very large compared to the volume, plus the body size is small. If this is there, then what happens is the temperature gradient exists in the body is negligible, means the temperature gradient which we are observing, that is very negligible, means we can say that the entire body is observed at the same temperature. It means that for this kind of cases, we can consider that the internal resistance offered or conductive resistance offered is negligible, means this kind of body will act as a body with infinite thermal conductivity. So friend, I hope it is very much clear to you. It is clearly mentioned the case physical size of body is very small, means we are talking about the solid for which surface area is very large compared to the volume. The example includes plate, bar, thin metallic wire. In this case temperature gradient is negligible, and in this case for this kind of small bodies the uniform temperature is observed throughout the time, means the internal resistance offered, that is L upon AK for Cartesian coordinate system, is assumed to be very small or negligible compared to the external resistance, that is a convection resistance of the surface. So we can say that the convective resistance is the controlling resistance, that is controlling the heat transfer. So when we are talking about this kind of cases, the convection resistance offered is controlling the heat flow, and this process is known as a Newtonian heating or cooling process, because we are talking about convection heat transfer, and the basic principle for the convection heat transfer or the governing laws for the convection heat transfer is Newton's law of cooling. So here it is mentioned Newtonian heating or Newtonian cooling process, and such analysis is called lump parameter analysis. We are talking about approximate solution because the whole solid will act as a solid whose temperature does not vary with variation in the time. So that thing is mentioned whose heat transfer at any time is a function of its temperature, and total heat capacity is treated as one lump, means the entire body is at same temperature. So friend, I hope it is very much clear to you what is meaning of infinite thermal conductivity, or what is the meaning of negligible internal resistance, what is called lump parameter analysis, and what is called lump. So everything what we had discussed, same thing is mentioned in this in the slide. You can refer it again and you can clear your concept very much. So now you can see we are talking about a body. You can see the figure with A. This is this body, that is our general system, in which we have to go for analysis of unsteady state heat transfer. So we are considering this as a body for which its physical size is small, and hence surface area to volume ratio, that is high. And here you can see for this kind of body temperature gradient is negligible, and because of that what you can observe is in negligible internal thermal resistance or conductive resistance is negligible. So the energy which is leaving, that is energy heat that is dissipating, that is mainly governed by convection heat transfer, that is HA delta T. And what also you can observe here is this is a body, this is a control surface, this is our system, where when time is 0, at that time temperature is equals to initial temperature. So here body is at initial temperature when time is 0, like you can say the metallic billet is there or metallic rod is there, that is at 1000 degrees Celsius in the furnace. When time is 0, the furnace is at, you can say, 1000 degrees Celsius, and the metallic rod is at 1000 degrees Celsius. As soon as you keep the metallic rod out from the furnace, where surrounding air is, you can say, 30 degrees Celsius, immediately the temperature of metallic rod will vary. So here it is mentioned that when time is more than 0, when you put the metallic rod from the furnace, immediately what you can observe, temperature is a function of time. More is the time you keep the metallic rod into the atmospheric air, temperature is dropping drastically. So what you can see, initial temperature is definitely higher than the air temperature. So initial temperature of metallic rod Ti is very high, you can say 1000 degrees Celsius. Metallic rod what we are discussing, and Ta, that is the surrounding air temperature. this Q convection, that is H delta T, that is also equals to minus rho Vc dt by d tau. So that is called mCp delta T. So mass into specific heat. So mass is replaced by density into volume. C is the specific heat. dt by d tau, that is a variation of temperature with variation in the time. So the figure A, that is general system for unsteady state heat conduction, is very much clear to you, where T is any temperature when time is more than 0, Ta is the atmospheric air temperature, rho, that is the density of this solid material, V, that is the specific volume of the, V is the volume of this material, C is the specific heat of this material, dt by d tau, that is a variation of temperature with reference to time. So if we'll talk about this equivalent thermal circuit, you can see the resistance offered, that is the convection resistance offered, that is 1 upon H into A, that is the convection heat transfer coefficient into surface area. CTS, that is the thermal capacitance, that is rho Vc. Ti, that is the initial temperature. Ta, that is surrounding air temperature. So when switch S is closed, the system is completed, the heat will start to flow from the system. The resistance offered, that is the convection resistance offered, that is 1 upon H into As. And as soon as the switch is kept open, the heat must not flow through the resistance, and through this capacitor all heat will be stored into the capacitor. So heat that will be stored into the system, that is CTH, that is rho Vc, that is density, volume and specific heat. So this equivalent circuit, I hope that is also clear to you. Because of this temperature difference between Ti and Ta, the heat will flow through this system, and that will flow from this path when switch S is closed. When switch S is open, all the heat that will flow through this capacitor, and that will be stored into this CTH, that is thermal capacitance. So what we had discussed, same thing is mentioned here. The rate of heat flow out of the solid body through the boundary, that is, you can say H A delta T, that is heat transfer by means of convection, where H is the convection heat transfer coefficient, As, that is the surface area, T, that is temperature at any time tau, Ta, that is surrounding air temperature, and that is equals to, you can say, the rate of decrease of internal energy of the solid, that is rho Vc dt by d tau with negative sign. So you can see m, that is equals to mass of the solid body, that is rho into V, where rho, that is the density of the solid, kilogram per meter cube, V, that is the volume of body, meter cube, C, that is specific heat of the solid body, unit is joule per kilogram degree Celsius, dt by d tau, that is the temperature variation in with this time tau, unit is degree Celsius per second, T is the temperature of the body at any time, unit is degree Celsius, H is the convection heat transfer coefficient, unit is watt per meter square degree Celsius, As, that is the surface area of the body, unit is meter square. So what we had discussed in the thermal circuit and schematic diagram, all that thing were mentioned there. Along with that, you can see Ta, that is surrounding fluid temperature, either it is a brine solution or it is a water or it is a air, unit is degree Celsius, and tau, that is the time in terms of second. Now we know that when time is 0, when tau is 0, at that time the solid is at Ti temperature, that is at initial temperature, and definitely it is mentioned here that Ti is greater than the surrounding temperature, that is it is more than liquid bath temperature or air temperature Ta. So this is heat that is transferred from the body to the surrounding, and that is equals to the amount of heat which is decreased. That is negative sign is indicating the decrease of internal energy. So Ha delta T, that is equals to minus rho Vc into dt by d tau, where we know that theta, that is the temperature axis, and that value is T minus Ta. So if I write theta T, I have to write T tau into T tau minus Ta. So if I will go for d theta by d tau, that is temperature axis is differentiate with the time, we will get what is the answer, dt by d tau, because we want to put what is the value of dt by d tau in terms of theta, that is temperature axis. So we know that this dt by d tau, that is theta, sorry, this dt by d tau, that is d theta by dt, and t minus ta, that is theta. So when I am rearranging this thing, I will get d theta by theta, that is equals to minus Ha divided by rho Vc into d tau. So what we have to do? We have to go for integration of this equation, because here differentiation is there. So we want to go for simplification. So we are integrating on both the side. So we will get ln theta, that is log base e theta, that is equals to minus Ha divided by rho Vc into tau plus C1. So C1 is the integration constant. And as you aware that to find out the integration constant, we have to apply the boundary condition. So now let us apply the boundary condition. Okay, so what we discuss is our initial condition is when time is 0, at that time temperature is initial temperature. So when we put the value, what we'll get, C1, that is the integration constant, that is equals to ln Ti minus Ta, that is equals to ln theta I. So when I am putting the value of C1 here, I will get ln theta, that is equals to minus Ha divided by rho Vc into tau plus ln theta I. So when I will put this theta I on other side, that is ln theta minus ln theta I, that is nothing but log base e theta divided by theta I. And when I am going for exponential power on both the side, or when I am going for putting e on both the side, you can say I will get theta divided by theta I, that is t minus ta divided by ti minus ta, that is equals to exponential power of Ha divided by rho Vc into tau with negative sign, where this is our final equation, in which T, that is the temperature at any time tau, Ta, that is the surrounding fluid temperature, either it is air temperature or brine solution temperature, or it is a water temperature, Ti, that is the initial temperature of the solid, again Ta, that is the surrounding fluid temperature, S, that is the convection heat transfer coefficient of surrounding fluid, As, that is the surface area of solid body, rho V and C, that is the density, volume and specific heat of the solid body, this tau, that is the time. So this is our final equation for transient heat transfer or for unsteady state heat transfer. So from the graph you can understand when the time tau, that is you can say with rise in the time, when we are going for the heating, what you will observe, temperature of the body is continuously go on increasing, and when we are going for exponential cooling, with increasing the time, the temperature of body is continuously decreasing. So what we had discussed, same is concluded here. So the equation what we had discussed, in which you will observe Ha divided by rho Vc into tau is there. So from that part you can understand the time is required for the solid to reach some temperature is there, means when the body want to achieve some temperature, definitely some time is required, and when the time is increasing continuously, either the body temperature is increasing or the body temperature is continuously decreasing. Now if the value of HA divided by rho Vc is large, in that case the body will approach to the ambient temperature in short time, means quickly the body will reach to the ambient temperature, and the quantity rho Vc divided by Ah has the dimension of the time, and that is called thermal time constant. This is called thermal time constant rho Vc divided by Ah, and that is known as tau Th. That is thermal time constant, and its value is indicative of the rate of response of the system to the sudden change in the environment temperature. Means you can say the metallic billet, or you can say a metallic wire which is in the which is in the furnace. All of a sudden, if its environment will change, if it is kept into the surrounding fluid, either it is a brine solution, air or water, how it will respond, that is called thermal time constant, and that rho Vc divided by A into H, that is indication of rate of response of the system when all of a sudden the solid temperature, that is environment temperature, will vary. So if I will rearrange this equation rho Vc divided by Ah, I can write 1 upon Ah into rho Vc, where 1 upon Ah is nothing but thermal resistance offered, and rho Vc, that is a thermal capacitance. So tau Ts, that is a thermal time constant, is, you can say, a multiplication of thermal resistance and thermal capacitance. So the same thing is mentioned here, RTS, that is thermal resistance to the convection heat transfer, and CTH that is the thermal capacitance, that is stored internal energy. So this lump system analysis can be visualized as an electrical analogy in terms of the resistance capacitance, that is RC circuit, and the process of heating and cooling as charging and discharging of the capacitor. So we had discussed the electrical analogy in the initial figure, where there is a charging and discharging of the capacitor, plus in the RC circuit we can tell heating or cooling as a charging and discharging of the capacitor, and the electrical analogy is also carried out. So that we had discussed. Now the term HA upon rho Vc into tau, that is, we have to rearrange it, and when we will rearrange, we will get two very important dimensionless numbers. So that is very important for conduction heat transfer transient analysis. So you can see the term HA upon rho Vc into tau. So this term I am rearranging, means what I am doing is I am multiplying V on numerator and dividing the same V in the denominator side. In the same way, I am multiplying the surface area in the numerator and in denominator. So what you can see is H into V divided by K into A, that is one term, and the second term what I will get is A square into K divided by rho V square into C into tau. So simply I did the exercise, multiplied V on numerator and denominator, multiplied surface area in the numerator and denominator, multiplied thermal conductivity in the numerator and denominator. Simply this exercise has been done. So what I will get from the first term is this part. H Lc by K from the first term, and from the second term I will get alpha into T, T that is alpha into tau divided by Lc square. So what is alpha? Alpha is nothing but the thermal diffusivity, that is K divided by rho C, that is thermal conductivity upon heat capacity. We had discussed in detail about this part. The detail is given in the description box, so you can refer that video, and you will get what is called thermal diffusivity. What is the significance of thermal diffusivity? So here alpha, that is K upon rho C, and Lc is the characteristic length. So what is characteristic length? That is volume of the solid divided by surface area of the solid. So this volume upon area, this again area divided by volume. This is Lc, characteristic length. Okay, so this is Lc, that is nothing but volume of the solid divided by surface area of the solid, and this characteristic length will vary, or it is different for different shapes. You can see for the plate, characteristic length is the volume divided by surface area. So volume is LBH, surface area is 2BH. So what is the LC value? Characteristic length, that is L by 2, that is semi thickness. If we talk about long cylinder, volume is pi r cube into L, surface area is 2 pi r. So what is characteristic length? R by 2. If we talk sphere, it is 4 by 3 pi r cube volume, area 4 pi r square, characteristic length is R by 3. Cube, volume is L cube, surface area 6L square. Answer L by 6, that is the characteristic length, where L is the side of the cube. In the same way, if we talk about long plate, the volume is area into length, perimeter is 2 into area. Sorry, volume is area into length and area is 2 into A, that is the surface area. So characteristic length is L by 2, where L is the thickness of the plate, and A, that is the surface area of the plate on one side. So friend, you can see here for different shapes, the characteristic length value is different. So what is characteristic length? That is the volume divided by surface area. So the first separation which was available with us, that was H into Lc divided by K, and that H into Lc by K is nothing but a Biot number. This is a dimensionless number, very important number. It is a ratio of internal resistance of the solid to the heat flow to the convection resistance to the surface. That is internal resistance or the conductor resistance divided by convection resistance. It is the internal resistance, or you can say conduction resistance, to the external resistance, that is convection resistance. So Biot number is H Lc by K, where H is the convection heat transfer coefficient of the surrounding environment. Either you can say it is a convection heat transfer coefficient of air or water or brine solution. Lc is the characteristic length, that is volume divided by surface area of the solid, and K, that is nothing but the thermal conductivity of solid material. Very important, K is the thermal conductivity of solid material. Now this lump capacity analysis can only be applied. This lump capacity analysis can only be applied when Biot number is less than or equals to 0.1. This is a very important thing. Biot number is less than 0.1 and the error associated with is around 5%. This criteria indicate that the internal resistance of the solid, that is the conductive resistance, is very less compared to the convection resistance when the heat is flowing through the surface. Means the internal resistance value is very less compared to the external resistance when the heat is flowing from the solid body to the surrounding. And when the Bard number value is less than 0.1, then and then we can go for lump capacity analysis, and the previous one was Bard number. The second one which we had discussed, alpha tau divided by LC square, that is nothing but a Fourier's number, and the Fourier's number is defined as the ratio of rate of heat conduction to the rate of thermal energy stored into the solid. What is the importance of this Fourier number? It is a very important thing. It signifies the degree of heating or cooling effect through the solid, or the degree of penetration of heating or cooling effect through a solid. So up to what depth you can say from the solid to the center the heat is penetrated, or the depth up to which the cooling effect is penetrated into the solid, that is indicated by the Fourier number. So I hope this is a very important thing. Fourier's number, that is alpha tau divided by LC square. This is again a dimensionless number like a Biot number. So I can write T minus TA divided by T0 minus TA, that is equals to e raised to minus HA divided by rho VC into tau, that is nothing but e raised to minus Biot number into Fourier's number. So this equation which we are observing at present is the equation for transient or unsteady state heat transfer for the solid body, where this Biot number and Fourier number are dimensionless number. T, that is the temperature of the solid body at any time tau, TA, that is surrounding fluid temperature, Ti, that is initial temperature of the solid, Ta, that is air temperature or surrounding fluid temperature, H is the convection heat transfer coefficient of surrounding fluid temperature, As, that is the surface area of the solid body, rho, that is the density, V, that is the volume, C, that is the specific heat of the solid, tau, that is the time, and that is equals to e raised to minus Biot number into Fourier number. So this equation is a very important equation for transient heat transfer. Now based on that we have to solve some numerical, and the first numerical which you can see at present is a steel ball. You can see that is of 550 millimeter in diameter and 900 degrees Celsius is placed in air of 30 degrees Celsius. We have to calculate the initial rate of cooling of ball in degrees Celsius per minute. So you can see friend, at present is density is given for this steel ball, that is 7800 kg per meter cube. Specific heat is also given to us, that is 2 kilojoule per kilogram degree Celsius, and the convection heat transfer coefficient value is also given, that is 30 watt per meter square degree Celsius. You have to neglect the internal thermal resistance. When this is given in the data, means immediately we must understand this is a problem related to unsteady state heat transfer, or from this data we can understand the ball which is at 900 degrees Celsius that is placed into the air. So immediately when the time is more than 0, immediately the temperature start to vary. So this is a transient heat transfer. What is given to us is the radius is 25 mm. So we have to convert that into meter. Initial temperature is given 900, surrounding fluid temperature is 30, density is 7800 kg per meter cube, specific heat we have to convert into joule per kilogram degree Celsius, convection heat transfer coefficient is given, time is given 1 minute, that is 60 seconds. So friend, this is a very simple case, but this is actually the case which we can observe in our real life, or the case which we can observe in the industry also. So what we have to do is, first we have to find out what is the value of HA divided by rho Vc into tau. Because the equation which is available with us, in which first we try to find out what is the value of this parameter. So you can see HA divided by rho Vc into tau. So AS, that is the surface area, a ball is there, so we have to consider volume, that is 4 by 3 pi r cube, surface area, that is 4 pi r square. This density is not there, actually it is not there. Okay, so we will get it is 3h tau divided by rho rc. So we know h value, we know tau, that is time, we know density, we know r value, what is the radius, and we also know what is the tau value. So everything which is required, that is available. So from that we will get the answer HA divided by rho Vc into tau value, that is 0.01385. So we have to find out what is the temperature. Surrounding temperature is 30, initial temperature is 900, HA divided by rho Vc into tau value is known to us. So we will get the rate of we will get the T value, that is 30 plus 0.9862 into bracket 900 minus 30, that is 888 degrees Celsius. So what is the rate of cooling? That is 12 degrees Celsius per minute. So this is our required answer. We can understand how fast the steel ball loses its heat when it is kept into the surrounding from 900 degrees Celsius to 30 degrees Celsius air. So friend, I hope this is very much clear to you how to solve this kind of numerical when you can say unsteady state heat transfer is given. Now this is a very you can say example containing routine life story. So it is given that an egg with a mean diameter of 4 cm initially at 20 degrees Celsius is placed in the boiling water pan for 4 minutes and found to be boiled as per the customer's taste. So initially the egg, which is of 4 cm in diameter, initially at 20 degrees Celsius, that is placed in the boiling water pan, means water is at 100 degrees Celsius for 4 minutes, and found the taste is satisfying the customer demand. Now for how long should a similar egg from the same consumer be boiled when it is taken from the refrigerator at 5 degrees Celsius? So the first case is the case where the egg is kept into the normal environmental condition, and the second case is where the egg is there in the refrigerator, and we have to satisfy the same customer, so there is no change in its taste. The properties for the egg is given: thermal conductivity, density, specific heat, and convection heat transfer coefficient. It is clearly mentioned, use lump theory. So if you will not calculate Bayes number, no problem. Otherwise we have to calculate Bayes number, and if it is less than 0.1, less than or equals to 0.1, then and then we have to go for unsteady state heat transfer. So the radius is available in millimeter, convert into meter. Initial temperature is 20 for first case, time is 4 minutes, so 240 seconds. Thermal conductivity is given, density is given, specific heat is given, and H is given. So if we calculate Bayes number, even though it is not necessary because it is directly mentioned, go for lump parameter analysis, but if we calculate it, how to calculate it? Characteristic length, that is volume divided by surface area, for egg 4 by 3 pi r cube divided by 4 pi r square, so it is r by 3. Bayes number is HLC by K. Convection heat transfer coefficient, characteristic length, and thermal conductivity, so it is 0.067, that is less than 0.1. So we can go for lump theory. It is not hemp, it is lump, LUMP, lump theory. So now what is the temperature variation in the first case? Quickly we can see the formula which is known to us, T minus TA divided by Ti minus Ta, that is equals to e raised to Ha divided by rho Vc into tau. This rho which you can see, it is actually not there. Okay. So H into As, that is the surface area, divided by rho Vc. So H upon rho C, As into V. So we will get the value of Ha divided by rho Vc. Tau is a 240 second. So T minus Ta divided by Ti minus Ta, that is e raised to minus 0.0025 into 240. So we will get T, that is equals to 82.16 degrees Celsius. So after 4 minutes the temperature is 82.16 degrees Celsius, which satisfy the customer's taste. So now for second case we have to find out for what time duration we have to put egg into the boiling water pan so the same taste is satisfied, or same customer is satisfied with the same taste. So initial temperature is 5 degree, as it is kept, it is taken from the refrigerator. It is kept in the pan, so surrounding fluid temperature is 100. We have to maintain 82 degrees Celsius. So 82 minus 100 divided by 5 minus 100, that is equals to e raised to minus 0.00625 into tau. So we will get tau, that is time duration. When we will go for this analysis, you can see when we will go for analysis, we will get the tau, that is 266.13 second, that is 4.435 minute. So when we are taking the egg from the refrigerator, which is at in which the egg is at 5 degrees Celsius, we have to boil the egg up to 4.435 minutes. That is, instead of 240 second, we have to boil it for 266.13 second. So same taste is maintained. So friend, you can understand what is significance of unsteady state heat transfer in real life also, and the numerical which we had discussed, that was related to real life. First steel ball, that was related to industry. Second was related to real life. Third again you can see that is related to industry, where in the data it is given that determine the time required to heat the steel plate at 20 with the 24 mm thickness from the initial temperature of 25 degrees Celsius to final temperature of 450 degrees Celsius by plating the plate into the furnace at 600 degrees Celsius. Take the following property of the steel. Thermal conductivity 45.4 meter per second, watt per meter degree Celsius. Cp, that is specific heat, that is 0.5 kilojoule per kilogram degree Celsius. Density, that is 7800 kg per meter cube. And H, that is convection heat transfer coefficient value, that is 23.3 watt per meter square degree Celsius. So friend, this is again a case where the initial temperature of plate is 25, the furnace temperature is 600. We have to put this plate into the furnace and we have to achieve the temperature 450. The plate dimensions are given and we have to find out what is the time required. So at that time this temperature is achieved. So you can see the thickness is given in millimeter, we have to convert into meter. This thermal conductivity value is given, so unit here is not mm, it is watt per meter degree Celsius. Watt per meter degree Celsius unit is there. Initial temperature is 25, surrounding temperature is 600. We want 450 temperature. Cp, that is a specific heat, that is 0.5 kilojoule per kilogram degree Celsius. Density is given, convection heat transfer coefficient value is given. we have to find out tau. So friend, now it is very easy, simple to us. So what we have to do is simply we have to calculate what is the Bard number. If it is less than 0.1, we have to go for lump capacity analysis. So the Bard number, that is HL by K, will put value of H, L and K. So we will get the value of Bard number, that is 0.00615, that is 2 less than 0.1. So we go for lump capacity analysis, that is lump capacity analysis. So you can write here T minus TA divided by Ti minus Ta, that is equals to e raised to minus H A upon rho Vc into tau. So don't go for this formula, it is derivation of H A upon rho Vc into tau with the negative sign. So no need to worry about this formula, directly go for this formula, e raised to. Okay, so put all the values, that is 450 minus 600 divided by 25 minus 600, that is equals to e raised to minus Ha divided by rho Vc into tau. Put all the values, so that is 150 divided by 575, that is equals to e raised to, you can say, tau divided by 4000, and so we will get tau, that is around 4000 into 1.34 divided by 3600, this is 3600, that is 1.5 hours. So after 1.5 hours we will get the temperature 450 in the furnace, which is at 25 degrees Celsius, and where initially the plate was at 25 degrees Celsius. So this was nothing but an application which is very much helpful in the industry where we want to go for heating of the metallic plate. Okay, so friend, in this video we had discussed about unsteady state heat transfer. We had discussed what are the different examples of unsteady state heat transfer, what is unsteady state heat transfer, what is the periodic variation in the time, non-periodic variation in the time. We had discussed lump capacity analysis. We had also discussed about Bayard number, Fourier number, and at the end we had discussed about the numerical related to unsteady state or transient heat transfer. So at the end, I would like to tell you that if you like this video, do not forget to subscribe and share this video to your friends, to your relative, to your student, so at free of cost they can enjoy the free lectures. And do not forget to subscribe this channel. To subscribe this channel, either you can scan this QR code or you can directly type AVM Tech Android in the YouTube and you can subscribe this channel. So like this video, share this video, subscribe this channel, and give the advantage to the student who really need this kind of video. Thank you very much.